So, in the last video we were looking at the converse part of the converse part, that is the sufficient condition to see the given differential equation is exact. Okay. So, that is you look at the condition dou m by dou y equal to dou n by dou x. So, if once you see that this is verified, we have seen that it is a necessary condition. If the equation is exact, this is a necessary condition. You want to check whether it is a sufficient condition. So, if dou m by dou y equal to dou n by dou x, then will I be able to get some u, so that du equal to 0, total derivative of u, this function u of x y, will it be du equal to 0 is the given differential equation. Okay. Let us continue where we left in the last video. So, if you start with, if you think that there exists some u satisfying this, okay. So, if I make use of this condition, will I be able to get my u? Okay, that is the question. So, if I use that, what is that you can use? So, now to make use of this result, I use dou u by this. What I do is I integrate this with respect to y, differentiate with respect to y, differentiate the above with respect to y. We get what we get, dou u by dou y is a function of two variables, and you are differentiating with respect to y, is dou u by dou y, and this is a function of y is involved, that you can take it inside, but let me write only outside. So, dou y of x naught to x m of t y dt plus this is only function of y, it is like derivative dg by dy. So, g dash of y I write. Okay. Now, what is this one? Dou u by dou y is like n. Okay. So, this is actually your n, it is actually your n, fine. Now, this implies n minus dou y of x naught to x m of t y dt is only function of y. So, this implies g dash of y equal to n of x y minus x naught to x dou m by dou y. So, because this is a function of y, this is the y derivative, so this is only function of x. So, I can take it inside dou m by dou y of t y dt equal to g dash y we have written. So, this you can get it if you integrate. Now, this is equal to n minus integral x naught to x. What is dou m by dou y? That is what I use now. Dou m by dou y is dou n by dou x, dou n by dou x of t comma y dt. Okay. So, now if I integrate both sides with respect to y, okay, integration with respect to y gives integral of g dash of y dy. Now, I do from y naught, that x naught y naught is fixed, y naught to y, okay, equal to n. So, n is function of x y. So, I do y naught to y n of x y dy minus, so this becomes what? So, this now so what you have is the dou m by dou y of t y, function of t y. So, this should be dt. Okay. So, I made this mistake. So, you have dou m by dou y function of t y, it will become dou n by dou t t y, variables are x y. dou m by dou y equal to dou n by dou x when it is a function of xy. Now, it is a function of ty, I have dou n by dou t. So, this is actually equal to n minus, as already you have n of xy, right, n of xy minus plus n of x naught y, okay. Plus n of x naught y. If I simply integrate dou n by dou t dt, so this goes simply total derivative of n at x, that is n at t variable, n at x y, n at x naught. So, n is a function of x y, this goes, this is simply n of x naught y. So, if you can integrate directly, so this right hand side is simply what you have is n at x naught y. This you are integrating with respect to y naught to y dy. So, this will give me my g of y minus g at y naught equal to this y naught to y n at x naught y dy. So, this I can replace as some dummy dt dt, t is a dummy variable. So, this will give me exactly what is my form of gy. So, gy is integral y naught to y n of x naught to t dt plus this g of y naught. So, I am actually solving this equation where g is unknown, okay. So, now g at x naught, g at y naught is an arbitrary constant. So, you can write it as arbitrary constant or write it as it is, g at y naught is an arbitrary constant. Actually, this is an arbitrary constant because g is unknown. So, this g you go and put it into your equation, you know what exactly the form it takes. U is this, you put it here, u is actually u form is this. So, this u is, now this implies u of x y which is equal to integral x naught to x m of x t dt or x ty dt, m of t y dt plus gy, that gy I can replace with this, that will give me y naught to y n of x naught to t dt plus this constant c, where c is g of y naught. G is, since g is arbitrary, at some point it becomes a constant, so it is an arbitrary constant, arbitrary constant. So, what I got finally, if I use that condition dou m by dou y equal to dou n by dou x, then I can get the equation, I can find some u that makes the equation exact, right, that is what is the converse, right. So, this is exactly such a function I constructed, okay. So, it is already here, so let me not write again. So, this is what is your function. So, what is this function? Once you have this function, this du, right. So, this implies given differential equation m dx plus n dy equal to 0, I can write m as dou u by dou y, this whole thing dou u by dou x, n as dou u by dou y, that makes it du equal to 0. That means u equal to constant is the general solution of the equation. What is u? U is here. That implies x naught to x m t y dt plus y naught to y n at x naught t dt plus c equal to, so let us say this is another arbitrary constant. When you integrate this both sides, what you have is arbitrary constant, okay, c1, where c1 is arbitrary. So, what you have is c equal to c1. So, this is equal to, this gives me this I can bring this c other side. So, both are arbitrary constant, together is also is an arbitrary constant. This is finally I can write C2, okay, which is actually C1 minus C, which is equal to C2, where C2 is an arbitrary constant. Okay. So, this is now function of x and y with an arbitrary constant. This is your general solution. So, that is how I got, because this is a general solution, I replace u with this. So, that is your general solution. This is the general solution of the equation, of the given equation m dx plus n dy. So, this is equivalent to say that this is the general solution of the equation. Okay. So, if you look at this form, you have, this is the equation m dx m of x y n of x y, okay, dy equal to 0. So, what you are doing is finally whenever dou m by dou x equal to dou m by dou y equal to dou n by dou x, that condition whenever it is satisfied, okay, that means if dou m by dou y equal to dou n by dou x, then the general solution is how we get it, you can see this m, you are keeping y as it is, you are integrating only with respect to x, you can see this m, you are integrating with respect to x, y you keeping as a variable. So, whatever may be, whether y is there or not, you simply integrate the term involving the coefficient of dx, that is the term m, you simply integrate with respect to x from some x naught to x, definite integration. So, you can fix your x naught y naught as 0 in practice. Okay. So, you can simply integrate with respect to x this m, and n you can simply see n, what happens, you fix x naught and you integrate with respect to y, other variable. That means you are putting x is 0. If you put x equal to 0, x naught equal to, if you take x naught equal to 0, that means n may become 0. Okay. So, in practice you have to integrate this with respect to y, only terms that involving y, not only terms of y only you should integrate, that will contribute. Okay. You can see from this. From this I can conclude the general solution has contributions from m and terms of y, terms of only y, terms of y only in x, in n. Okay, you can see this. That is how you get the general solution. Whenever you check this condition, once this condition is satisfied, you know that it is an exact. The shortcut to find the solution is m you integrate with respect to x, keeping y as it is, and here you put x equal to 0 and you integrate. Once you put x equal to 0, n may become 0. When you have only terms of y, even if you put x equal to 0, those terms will remain, you simply integrate it with respect to y as if x is not there, okay, by putting x equal to x naught. That is how you can directly get the solution like this. Okay. In summary, what we had is, given a differential equation like this, it is an exact, this is the definition. So, m and n I should be able to write in terms of partial derivatives of some function u of x y, that is the definition. If suppose this is exact, suppose that means I can find such a u satisfying this, immediately I have this condition is satisfied. So, this is a necessary condition, necessary. For an exact equation, this condition is necessary and is also sufficient. What a converse is the sufficient condition. What is the sufficient condition? If this is satisfied, my equation is exact, that means I will be able to find my u satisfying this. Okay. Such a thing I constructed by assuming that it exists. I used of the condition dou m by dou y equal to dou n by dou x. Okay. Finally, I derived the solution. Okay, as this. So, we will do some examples, you will understand. is here. So, example, you take this y plus 2x e power y dx plus x into 1 plus x e power y into dy equal to 0. How do we solve this equation? So, solve this differential equation is given. So, it is in the form of m dx plus n dy equal to 0, where m is y plus 2x e power y, n is x into 1 plus x e power y. Okay. If this is an exact equation, I know that necessary condition will give me dou m by dou y equal to dou n by dou x. What is dou m by dou y? It's simply 1 plus 2x e power y. What is dou n by dou x? 1 plus 2x e power y. Both are same. Necessary condition. If this is satisfied, that is clearly it is satisfied for these functions mn, I know that the equation is also exact, converse is also true, right. So, we do not, when you are given a differential equation, you do not know that you do not know a priori that the equation is exact. Okay. If it is exact, this condition is automatically should be necessarily it should be satisfied. Because the converse is true, that means this condition, if this condition is satisfied, that we have checked here, it is verified that it is condition is satisfied, that makes the converse is also true. That means a given differential equation is an exact equation. Okay. So, once you check this, we check this implies converse is true. So, the equation, given equation is an exact one. So, if it is exact, you know how to get the solution, general solution. We have seen just now some time back. So, you simply take m, you integrate with respect to x, you simply take n, you integrate with respect to y by fixing x naught. Here you do not fix y naught, okay. You add them, put equal to constant, that is the general solution of that equation, if this condition is satisfied. Okay. So, this implies the general solution is of the equation, the given equation is, what is m integral, I fix my x naught y naught as 0 0, okay. Let x naught y naught equal to 0 0, because they are defined. You look at the equation, 0 is 0 0, there is no issue at 0 0, there is no division with x y. So, x equal to 0 0 is part of the domain, I can choose my x naught y naught as 0 0. Okay. So, you integrate from x naught to x naught is 0 to x m is y plus 2x e power y dy dx. Okay. This is dx. Y I am keeping as a variable, x I am simply integrating with respect to 0 to x, okay, plus y naught, that is 0 to y, n is x plus x into x square e power y dy. I fix y naught, inside also n of x naught y, x naught is 0. So, if I put 0, this is 0, this is 0, 0 into 0, the whole thing is 0, okay, equal to constant. So, this implies if you integrate this now with respect to x, xy, okay, plus x square e power y, and this is 0 equal to constant. Okay. So, this is your general solution, with an arbitrary constant. C. In this video we have seen that the given differential equation So when it is exact equation, so if it is a once you are given a differential equation, you can just verify that dou m by dou y equal to dou n by dou x, then that is a necessary and sufficient condition. That means if your equation is exact, implies it is exact, this condition is satisfied. If this condition is satisfied, then also the equation is exact. So you can only check this condition and you can say that the equation is exact, then we can solve the equation. Okay? You have seen what is the form of u, what kind of form you have got. Okay? You have got for the u of x y. So that will give you, so we will do examples, some more examples in the next video.